students. Welcome to the video on the field effect transistors. Today's topic is small signal equivalent and frequency limitations. So as we have discussed in the previous videos, a JFET can be operated in linear region, and then it will be going to pinch off, followed by which the output current will be saturated. So we can vary the output current by changing the gate voltage. So it is called as an voltage control device, or it is otherwise called as a field effect transistor. So here, coming to the characteristics of JFET, the first important note is the drain current in the active region. So the note that the value of the drain current will be always between the 0 and the maximum, that is the maximum current IDSS. So here, by knowing the drain current ID and the drain to source voltage VDS, the resistance of the channel RDS is given by ID is equal to IDSS into 1 minus VGS by VP the whole square, where VP is nothing but the pinch of point. At the VP is the voltage at which my device goes to the saturation, starts the saturation, and VGS is the voltage which is across the gate to source terminal. IDSS is the maximum current flowing through the device, and ID is the current through the drain terminal. And also the drain to source channel resistance is given by RDS is equal to delta IVDS divided by delta ID, which is equal to 1 by GM. So GM is the transconductance gain, or it gives the gain of the transistor, that is the variation of ID with respect to VDS. Since the JFET is a voltage control device and which represents the rate of change of drain current with respect to the change in the gate to source voltage. So coming to the small signal equivalent circuit. So we know that any device can be represented for its analysis in terms of its the internal resistance and the capacitance. So here when I take an JFET, we know that it will be consisting of three terminals, namely the source, drain and the gate. So the gate terminal will be always a metal layer, or it is nothing but it will be a metal layer, or it can be some conducting material which is coated, and the substrate may be an gallium arsenide, or and it is it can be a p-type material here. And now the cross section of the JFET will be given as given in the first diagram. Here the source and drain are the two terminals which will be taken out from the substrate, and the internal resistance is given by RS and RD respectively. So these are the series resistance between the source and gate as well as from the drain and the gate terminal. The second diagram gives the small signal equivalent circuit of JFET. So here we can see that the RGS is the resistance, the internal resistance and the diffusion resistance of the device, and similarly RDS is the diffusion resistance of the drain terminal. Similarly, the capacitance is given as a junction capacitance CGS and CDS. So here we assume that the S is the source, it is a source terminal, and it is with respect to the substrate. And here the current source is given as GM into VG dash and into S dash. So here when taking in at low frequency, that is the above diagram will be reduced at low frequency as the capacitance become open circuited and the resistance value will become very minimum, and hence these capacitance and resistance in series can be, I mean in parallel, can be removed, and hence the equivalent circuit will be represented by this simple diagram. So here you will be having the gate terminal as well as the drain terminal along with the constant current source, which is given as GM into VGS. But when we consider the source resistance, that is the resistance from the source to the substrate, then the circuit will become Vg dash the voltage which is appearing across the gate and the substrate is given as Vg dash S dash, and hence the small signal drain current is given by IDS is equal to Gm into VGS. When I include the source resistance, source series resistance, then my IDS will become Gm into Vg dash into S dash. But from the second diagram, we know that VGS is equal to Vg dash S dash plus the voltage drop across RS, which is given as Gm into Vg dash into RS VGS dash S dash. So using these two above equations, we can derive that IDS is equal to Gm divided by 1 plus Gm Rs into VGS, which is equal to Gm dash into VGS. That is, finally, we can conclude that the effect of source resistance is just to reduce the effective transconductance or the transistor gain. That is, when I include a source resistance, when I include the source resistance, it will result in the reduction in the transconductance, or it will be reduction in the transistor gain. So that is given here in this graph. That is, when my GMS is considered, that is my uh, transconductance without considering the source resistance, we can see that my current will be decreasing exponentially with respect to the voltage, and the amount of current will be less when I consider when I the gain will be less when I consider the source resistance. The dotted curve will give me the transconductance versus the VGS with a source series resistance. So the next one is, what is frequency limitation factors and the cutoff frequency. There are two frequency limitation factors in a GFET. The first one is the channel transient time. If you assume a channel length of 1 micrometer and assume that carriers are traveling at a saturation velocity, then the transient time is in the order of A is equal to L by Vs, which is equal to 10 picosecond. Next limiting factor is the capacitance. To understand the capacitance of the effect of capacitance on the device, we will assume that all the resistance are removed and the capacitance are given as CGS, CGD, and here what is the effect? So now the second frequency limitation is the capacitance charging time. So the equivalent circuit includes only the primary capacitance and it ignores the diffusion resistance. The output current will be a short circuit current. As the frequency of the input signal voltage increases, VGS increases, the impedance also of the CGD and CGS decreases, so the current through the CGD will increase. For a constant GM-VGS, the IDS current will then increase. The output current then becomes a function of frequency. If the capacitance charging time is the limiting factor, that is, if capacitance plays a role in the frequency limitations, then the cutoff frequency will be decided by as a frequency at which the magnitude of the input current IA is equal to the magnitude of the ideal output current GM-VGS of the intrinsic transistor. So we can equate these two conditions and we can obtain the frequency, cutoff frequency of the maximum cutoff frequency. So when the output is short circuited, we can give here IA is equal to j omega into CGS plus CGD into VGS. But if you let CG is equal to CGS plus CGD, then the cutoff frequency is given by GM divided by 2 pi CG. So the maximum possible transconductance is given as GMS max is equal to E mu n NdWA divided by L, and the minimum gate capacitance is given as Cg minimum is equal to epsilon S WL divided by A, where A is the maximum space charge width. The maximum cutoff frequency can be written as F suffix T is equal to E into mu n NA square divided by 2 pi epsilon S into L square. So now in this video we have discussed what is the characteristics of the JFET, and we have discussed what is the small signal equivalent model? And we also have found that, or we have studied that the source resistance, when included in the circuit analysis, will reduce the transconductance or the gain of the device. And similarly, we also have seen that capacitance plays an important role in the high frequency operations. So here we have discussed in detail about the JFET, its operating principle and its characteristics curve.